Hi students, Professor Nugent here. In the next few videos, we're going to discuss the characteristics of OLS under measurement error. Measurement error occurs when an economic variable in a regression model has been measured imprecisely. For example, we may care about a marginal statistic, but only have information about the average. An example of this is marginal tax rates, right? We may want to think about the effect of marginal tax rates, but we only have information on average tax rates. Or we may want to think about the effect of marginal cost, but we only have information on average cost. Measurement error may also occur through anything self-reported, any information collected through surveys. There's bound to be some measurement error. The structure from measurement error in terms of the characteristics for OLS is similar to omitted variable bias. The bias is a concern for estimation of the variable of interest. And this really matters for variables for which we can collect when the data differs from variables that influence decisions. All right, so we're thinking about, for example, the marginal tax rate versus the average tax rate. We can collect data on the average tax rate, but it's really the marginal tax rate that influences decisions, because decisions are always made on the margin. Same with marginal and average cost. We can collect data on average cost, but it's marginal cost that influences decisions. So this kind of measurement error matters when the data that we can collect differs from the data that influences the variable that influences decisions. Now, the first kind of measurement error that we're going to think about is measurement error in the dependent variable. So let's let y star denote a dependent variable. For example, family savings. And y is the observable variable. Perhaps the self-reported amount of family savings. The Gauss-Markov assumption satisfying population regression function is the following. Y star is equal to beta naught plus beta 1 x1 all the way through beta k xk plus u. All right, so y star, that unobserved dependent variable, is the variable in the population regression function. Let's define the measurement error E0 as y minus y star, so the difference between the observable variable, like self-reported family savings, minus the actual family savings. We can rewrite this as y star is equal to y minus E0, and then plug this into the population regression function so that we have y minus E0 is equal to beta naught plus beta 1 x1 through beta k xk plus u, and then let's put the error on the other side so that we have y equals beta naught plus beta 1 x1 through beta k xk plus u plus E0. All right, so the error term becomes u plus E0. And we already have that U has zero mean and is uncorrelated with the explanatory variables because we said that the population regression function satisfies the Gauss-Markov assumptions. We can assume that E0, rather the expected value of E0 is 0, so it has zero mean, and is uncorrelated with the explanatory variables. So the covariance between E0 and X is 0. Okay? If this is true, then we have unbiased and consistent estimates. So these two things imply that OLS is unbiased and consistent, and our T and F stats are valid. If E0 and U are uncorrelated, then the variance of E0, U plus E0, this will be equal to sigma U squared plus sigma E0 squared. So the measurement error increases the error variance by this term. So we'll have larger error variance. The variances of the estimators will go up. If the expected value of E0 does not equal 0, this implies that we will not get unbiased estimate of beta naught, which is okay. We don't really care about beta naught. We care more about beta 1 through beta k. The real problem is that if the covariance between E0 and the x's is not equal to 0, so if E0 is somehow systematically related to the regressors, then the other coefficients, the beta 1 through beta k, will be biased and inconsistent. Now, the assumptions that E0 has a mean of 0 and is uncorrelated with the explanatory variables is reasonable if the measurement error is due to random reporting error. Random reporting error such as you would get from something like survey evidence. This is something that would be investigated in the process of any investigation or research. That is it for measurement error in the dependent variable, which is, as you see, as long as our assumptions are valid, not terribly consequential. Stay tuned to the next video. We will discuss measurement error in the explanatory variable, which can have worse consequences for our OLS estimators.